All right, welcome to the final example, example 5, alternating series. We're considering this alternating series from n equals 1 to infinity, negative 1 to the n minus 1 times 3 over 2 to the n times n plus 1. We want to first, part A, show that the series converges. How am I going to do that? It's not just geometric. If it only had the 3 and the 2 to the n in it, it would just be geometric. And then we could deal with this negative 1 business and get rid of it. But it's not, because it has this n plus 1 in it down here in the bottom, which means that we only have available to us the alternating series test. Part B, find the sixth partial sum and show that this value differs from S by less than 3 over 1,000. Okay, this is a very common thing that they ask us to do. They give us this weird fraction, and then we show that our sum is off. That's the remainder. We want to make sure that the remainder is less than that particular number. Okay, so then on example, I think it was 5. I'm going to write 5 and hope for the best. Good, it paid off. All right, and then my series here was from n equals 1 to infinity of negative 1 to the n minus 1? All right, if you say so. Times 3 over 2 to the n times n plus 1. All right, the first part is about convergence. Part A. And we have to use the alternating series test. And remember that the alternating series test has 2 parts to it. As long as our nth term, which is equal to 3 over 2 to the n times n plus 1, is greater than 0. Well, when we're sticking in numbers that are starting at 1 and getting increasingly bigger, that is definitely always a positive number, so that checks out. Okay, so now let's take the limit. Here's the first part. The limit as n goes to infinity of 3 over 2 to the n plus 1, what is that equal to? The top stays 3, the bottom just keeps getting bigger and bigger and bigger. That's going to 0. Check. All right, the first condition has been met. Now let's check the second one. We want to show that the n plus 1th term is less than or equal to the nth term. So you can either do it algebraically, or you can do it calculistically, that word that I made up. Let's just go ahead and try it algebraically. Let's see what happens. Anywhere there's an n, we're going to stick in an n plus 1. I'd have 3 over 2 to the n plus 1 times n plus 1 plus 1. That's n plus 2. I said 2 and I wrote 1. 2 is got to be less than or equal to 3 over 2 to the n times n plus 1. So, of course, what I want to do is I want to check to make sure that makes sense, because I don't know about your brain. My brain's not processing it. It's not obvious to me that one's bigger than the other one. So I can just cross multiply. Everything's positive here because my n value is 1 or bigger. So when I cross multiply, I would have on the left-hand side 3 times 2 to the n times n plus 1. Is that less than or equal to 3 times 2 to the n plus 1 times n plus 2? All right, is that true? Let's just start canceling stuff. Love to cancel stuff, like these 3's. I love to cancel that. And this 2 to the n, we can divide both sides by 2 to the n. If you were to divide 2 to the n plus 1 over 2 to the n, you subtract your exponents and you just get 2, right? N plus 1 minus the n gives you just 2. So bloop, bloop. That's really nice. So we're left with n plus 1 on the left-hand side. Why are we pink? Did I not change it? Really? Okay. N plus 1 is less than or equal to 2 times n plus 2. Maybe it's still not obvious to you. All right, so I'll distribute. N plus 1 is less than or equal to 2n plus 4? Still, maybe it's not obvious. So let's see. I am going to subtract over the n, and subtract over the 4 is less than 3. Yeah, okay, so that's definitely true. N is definitely greater than or equal to negative 3 because it's starting at 1. So this is true. for n is greater than or equal to 1. That's all we really care about because it's starting at 1. So check and check. Therefore, the sum from n equals 1 to infinity of negative 1 to the n minus 1 times 3 over 2 to the n times n plus 1 converges by the alternating series test. Make sure you spell the word series correctly. Now it doesn't even look right. All right, I don't have a spell check on my pen. Yeah, it definitely converges. So there's part A of that question. We were able to successfully show that our series converged. Now, part B, it says, find the sixth partial sum and show that this value differs from S by less than 3 over 1,000. All right, definitely not enough space here. Let's add an extra page. Add the page. I'm going to need lots of extra space here. Part B. I want to find, well, S sub 6, which will equal the sum from n equals 1 to 6. I'm just going to put this out on the outside. Negative 1 to the n minus 1. 3's on top, and on the bottom is 2 to the n times n plus 1. Well, I don't know about you. Why are you zooming? I don't know why. But I'm not going to do that by hand. I refuse. I'm going to put that into the calculator, just like I did the other one. So my summation from n equaling 1 to 6. Why are we always going up to 6? Who knows? All right, so put in our little fraction here. And in parentheses, our alternator, negative 1. Let's make sure that I get the exponent right this time. Raised to the n minus 1 power. Get out of the exponent. Multiply times 3. And on the bottom, we have 2 to the nth, not x. 2 to the n. Get out of the exponent. Times parentheses n plus 1. Pretty sure. Enter. 633 over 1120. YouTube. Why did I click on that one? 633 over 1120. If you don't like that, do you want a decimal approximation? Okay, I can accommodate that. There you go. It's about 0.565-ish. Okay, a little over a half. And now the actual part of this question, the big part that associates with the lesson is, hey, how far off are we? So if I were to take the absolute value of S minus S sub 6, the difference between our actual sum and the sixth partial sum which we calculated, that thing is equal to the absolute value of the remainder, which is always less than or equal to the next term, the first neglected term, the absolute value of it anyway, which for us should be the seventh term. And I can get rid of that absolute value if I just disregard the alternator that's there. So S minus S sub 6 is less than or equal to, I just have to physically put 7 in and evaluate it. So I've got 3 over 2 to the 7th times 7 plus 1. Now I just want to keep simplifying this because I have a number that I'm trying to zero in on and show that this number is less than that. I've got 3 over 2 to the 7, just ignore that for right now. And this is times 8. All right, you could put that into the calculator, but I know that 8 is 2 to the 3rd. 2 to the 7th times 2 to the 3rd. And all of this is 3 over 2 to the 10th. Now, 2 to the 10th, unless you speak binary, maybe you don't know that one. 2 to the 10th is 1024. So, S minus S sub 6, the absolute value of that is less than or equal to 3 over 1024. Did we do it? Let's come back right up here for a second. We needed to show that it's less than 3 over 1,000. Is that thing less than 3 over 1,000? It should be, because the top is the same and our numerators, our denominator is a little bit bigger. We're dividing it by a little bit bigger number, so that's true. Absolutely, we accomplished our goal. So, recap here. What we were able to do is show that our series converged by the alternating series test. In other words, the limit of the terms approach 0, and the terms are actually decreasing. The n plus 1th term is less than or equal to the nth term by just showing an inequality was true. And then we were asked to find the 6th partial sum. Used a calculator for that because I'm not adding those things up. And then use the 7th term to bound what that error is, what the remainder that was left off. Our sum for our sequence is off by no more than 3 over 1,024. Which brings us to the end of this alternating series test. We were able to see if a series converged by alternating series tests, and there are 2 components to that. You have to make sure that your terms are going to 0, approaching 0, and that they're decreasing towards 0. And we were also able to calculate the error in an alternating series approximation by just looking at the first neglected term.